Right, good afternoon. This is the CNTL class. Controls 2, Fenchurch College, London, Ontario. Welcome again. Right, so the last time we stopped at this slide right here, but I'm going to retrace it back a little bit because I just don't want to start this thing out of context. So we were talking about something that's called the integration of the transmission systems. All right. And the power transmission, according to what we are dealing with, is the primary term for the principles and the components. And here we're talking about integration, so it's going to be mechanical, electrical, hydraulic, and pneumatic systems, components used to transmit and control power throughout the system. So there's a bit of a mouthful. Does it tell us anything? Well, but we have pronounced it. Okay, so individually or in specific combinations, these systems can be classified under the following categories. So we have the fluid power, we have the actuation systems, and we have the integrated systems. We talked a little bit about the actuation versus the main power flow. So the main power flow would be the main air supply for the pneumatic system, or the main fluid supply for the hydraulic system. All right? And the actuation system would be actually the pilots. What's a pilot? Do we remember that? That is the thing that triggers. So pilot could be actually a trigger, or sometimes it is called actuator. Right? So we are triggering or actuating, and in the conceptual diagrams, or the pneumatic diagrams, or the hydraulic diagrams, those usually are, if somebody really wants to follow the rules and be really cute about that, those pilot lines would be drawn with the dashed or dotted lines, usually dashed lines, to indicate that this is not the main power flow, it's actually a trigger or actuator. Okay, actuation is what's actuating. Actuating is making things move, all right, triggering things. Actuation is movement. All right, so actuation systems as opposed to the main power flow. We did that today and yesterday during the theory class. So for the fluid power, more specific classifications that comprises the hydraulic and pneumatic to generate the control, okay, so you can read that later on. Read it 5 times until it gets, or better yet, go through all the labs, and then once you read that again, it actually is going to make some kind of a sense to you. All right, that's what my goal is. Actuation systems in industrial automation. These 4 technologies are the primary methods used to create physical movement actuation. Well, you see, if we didn't talk about the main powertrain system and the pilot lines and the actuation, this thing would not mean anything to you. But because we talked about it today, and section 4, I believe, already did the lab. So actually, you have, most of us have done the labs already, connecting the lines, so you can tell the difference between the main power system or the main air supply to make things move, and the triggering system or the piloting system or the inputs that actuate things, make them trigger. Like there's a valve that could be actuated by a push button. It could be actuated by a selector switch. It could be actuated by a solenoid or electromagnet, or it could be actuated by another pneumatic type of trigger. Okay, integrated systems. So because we're talking about integration, and here's a cute symbol that AI came up with. All right, so integrated systems, a term used for machines where these diverse subsystems are interconnected. For example, using an electrical signal to trigger a pneumatic valve, that moves in a mechanical arm. In industry, usually you're going to have not just one type of a machine that employs only one type of a system. You're going to have integration of things, and that's what we're trying to get you, ready with when you go and face the world. And what is the world is your oyster. All right, electropneumatic control. So, for example, here, this is all familiar symbol for us right now, except for this little guy right here. Remember, we have that. This is our actuator. Here's a symbol of. Remember what that would be. How many ports does this one have? 1, 2, and 3. Okay, so port 1, remember, is the main air supply. Port 3 would be the exhaust. Sorry, this would be port 1. This would be port 3, and this would be port 2. Remember, main air supply, in this case, this is blocked, so this valve is normally closed. This is the output, which would be port 2, and port 3 would be an exhaust. And remember, port 4, if there were more than 3 ports, port 4 would be the extra supply air, and port 5 would be the extra exhaust. So remember, we should all know what this one is. This is a valve. We can tell that this is a valve. How many ports? Well, we can tell it's 3. And is it normally closed or is it normally open? In this case, it's normally closed because here's the spring pushing that whole device into this resting position. And if we slide the whole thing by, well, if this were a push button, we would push that, so this square would find itself in this position here, so then the air would be passing through and the exhaust would be blocked. But in this case, it's resting position because there's a spring. It basically, it's considered as normally closed. How many ports? 3. How many positions? 2. So it's a 3 two-way valve, normally closed. And this little symbol here symbolizes a solenoid or electromagnet. So this, instead of being a push button actuated or triggered, it's triggered by electromagnet, or otherwise called a solenoid. Integration of pneumatic and electrical technologies is the title of this slide, or the subtitle. Now, with that, we have fast signal transmission because we have electrical signal triggering that. So we have a fast signal transmission. Electrical signals travel quickly over long distances, reducing delays in control systems. Okay, that makes sense. Flexible system design, easy integration with controllers or programmable logic controllers, PLCs, which we will also tackle as we go along. So easy integration with the controllers and PLCs allows for adaptable automation solutions. This statement here is going to become a little bit more clear a couple slides down the road. Okay, when we talk about the hardwired logic versus a programmable logic. Okay. All right. So now, when it comes to control, we get precise control solenoid or electromagnets, solenoid valves, and sensors enable accurate actuation and repeatable operations. All right, as we go along, this statement again is going to make more sense because we're going to experience that. All right, we're going to have the experiential thing going on here. Scalability. Systems can be expanded or modified easily to meet the changing production requirements. Again, when we talk about the difference between hardwired logic and the programmable logic, then this thing again is going to make sense. But because you're going to have this downloaded, you already have, you can go back to it and make sure that this thing makes sense. to you. All right, electro-pneumatic control, the real-world applications. Where is it that those things are being applied? Okay, industrial automation, assembly lines. So we're talking about the pneumatic control. All right, electro-pneumatic. So there's the pneumatic systems that are triggered by electrical systems. So there's a main powertrain in this here. There will be pneumatics, and the triggering of that would be electric. Right, so where do we have that? Assembly lines used to controlling actuators and robotic arms. In automotive and electronics manufacturing, just remember the difference between the pneumatics and hydraulics is pneumatics can be fast, but it is not as strong. Now hydraulic systems are slightly slow, well, significantly slower, but also they are way more powerful. All right. So, for example, in packaging machines, enables precise and fast, you see here, fast movement for sealing, cutting, and sorting, picking up papers, print shops, and all that. Well, large print shops, that's where they print the newspapers and things like that, or big sheets of paper baseball cards, for example, and all that stuff. Those are huge machines, but it doesn't take much power to lift a sheet of paper. Right? All right, material handling applications, conveyor systems, electro-pneumatic valves control air cylinders for delivering, diverting packages. When I did some work at one of the huge packaging systems in Vaughan, Ontario, I was on the boom lift, so I was up in the air doing some wiring in the ceiling there, and I was able to have the bird's eye view on all the sorting machines. It was actually entertaining to watch, and hydraulics were used to service that, sorting packages. Okay, pick and place robots combines electrical signals with pneumatic actuators for quick, accurate positioning. Pick and place robots. It picks something from one place and places it in another place. All right. Process control, real world applications, food and beverage industry. See, we're talking about not very. So there's a difference between picking up a bottle of pop bottle and filling it up. It takes way less power than digging a hole with a backhoe. Right. Automated filling and capping systems rely on electro-pneumatic valves. Okay, pharmaceutical production. See, pharmaceuticals when it comes to sorting and packaging, pills, for example, you need to have clean environment. And when it comes to air can be clean, and if more clearness or cleanliness is required, then other gases can be used other than air, but usually air would do it. Pneumatic production ensures clean, controlled actuation for dosing and packaging for the pharmaceutical industry. Transportation, railway systems, brakes, pneumatic brakes, or, did you ever hear the term air brakes? Well, there you go. Pneumatic brakes triggered by electrical signals for, safety and reliability, blah, blah. Automated doors, for example, electrical sensors activate pneumatic cylinders for smooth operation for the automatic doors. It all makes sense, doesn't it? And we talked about the sensors, so that was the last time we saw it. I'm just going to go quickly over this slide here. Here's a cylinder, and inside the cylinder there's a piston. The piston can be supplied with a magnet. All right, and then the magnet when the magnet inside the piston is placed over that little, in this case it could be something that's called a reed switch. And what's a reed switch? A reed switch is just like the, for example, all right, see my drawing skills. Here is, all right, Here's a saxophone with all the buttons. Okay, here's the buttons of the saxophone, and here's the mouthpiece. The mouthpiece has a reed. If you magnify that, it will have two plates that, if you blow the air through that cylinder, that involves having that those two little plates, they start vibrating, and that's called a reed. So, by the same token, a reed switch would be a couple of metal plates with connections, and if we put the magnets to it, all right, that those two touch, so that would be the reed switch. Reed switch. Those reed switches also are used in security systems for something's called door contact controls, magnetic controls. All right. So there will be a magnet there, and there will be a reed switch in here. And when the piston inside moves to a certain position, that can be placed to well, sense the position of whatever the rod would be and whatever it's attached to the rod. That would sense the position. You could have the position of fully retracted or retraction position, or and the extension position. Okay, Eric says that he can't see the screen that I'm sharing. Can you guys confirm that that's the case here? Okay, I think it might be you, Eric. Yes, it could be your equipment. Are you watching this thing on a tablet, cell phone, or a PC? PC. Well, that's interesting. You know what? Just toggle. Means log out and log back in. See if yeah. Okay, cool. I'm sad for Eric, but I'm happy for me because it's not my problem, right? Okay, cool. All right. Now, this is where we stopped last time. Electrohydraulic system. Now, electrohydraulic systems. So now, you see, we talked about the electro-pneumatic systems, and now we're going to talk about the electrohydraulic systems. Now, comparing to the pneumatic systems, we're going to have high power involved. High power density. That's the title of this phrase here. High power density can transmit large forces in compact spaces, ideal for heavy duty applications. All right, precise and smooth motion control. All right, because let's see here. Let's get rid of the saxophone. It is saxophone, okay? So here is a cylinder. Alright. It does have a piston in it. And the piston is connected to a rod that goes outside of the cylinder, and it's connected to whatever it is. If we have air here, if we supply the air, depending on the load and the force that needs to be applied to the load, that load can push back. Mr. Newton, there we go. Action and reaction. It's going to push back before it starts moving. So the air, because it's compressible, it is going to have some kind of like a delayed reaction. If this was not air, if it was a fluid or liquid, sorry, like oil, oils or liquids are considered incompressible as opposed to the air and gases that are considered compressible. The air is going to compress. It's going to have things are going to have a delayed reaction, which means we are not able to. It doesn't work well with transmitting large amount of energy or force, because oil is incompressible. That pressure that you're going to control here, if we move the liquid into this chamber here, it doesn't compress. There is no negotiations. There is no spongy or springy type of an action when we talk air or gases. When it's liquid, there is no compressibility. This thing moves, and if you don't want to be crushed, you better get out of the way. Now, so with oils or liquids, we do get a lot of power, but we don't have the speed. With air, we do have the speed, but we don't have the power. So there's something for something. All right. So precise and smooth control. Okay, here. All right. So high power density with liquids, because we're talking hydraulics. High power density can transmit large force in compact spaces, ideal for heavy duty application. Precise and smooth motion control. Electrical signals by hydraulic plus hydraulic actuation. So you can actuate a cylinder, which means you can trigger a cylinder with air. It could be a pneumatic actuator, but it could be a hydraulic cylinder. Because triggering doesn't take much power and it can be fast. But if you have electrical triggers, the electrical signal can be fast, and the hydraulic actuation could be precise and powerful. So we're talking about accurate positioning and smooth operation here. Remote and automated operation. Electrical controls enables easy integration with PLCs, programmable logic controllers, and sensors for remote monitoring. All right, so combining the hydraulics and electrical systems, we can get the best of both worlds. Right? Plus, electrical signals can be transmitted over longer distances. You can transmit electrical signals across the continent. Try to build a pipe that moves air from China to Africa. Right. All right. Flexibility. Will you post these recorded? Yes. Yeah, I'll be posting them. They're already there. Right. The first part. So flexibility in design. Okay. Electrical hydraulic control systems, or electro-hydraulic systems, can be adapted for complex tasks, including variable speed and force control. Naman, it is what it means. All right, it's quite self-explanatory here. Energy efficiency, controlled hydraulics power reduces energy waste compared to purely mechanical systems or hydraulics. Controlled hydraulics. Well, we have energy consumption issues here that can be resolved easily by implementing that. Safety and reliability, blah, blah, blah. You can read that. Next slide. Hydraulic and electro-hydraulic control, real-world applications. Okay, so we're talking about heavy machinery, excavators, backhoes, loaders, cranes, press machines. In aerospace, air flight control. Pick and place robots combines electrical with pneumatic actuators for quick and there's a repeat a little bit here. Automotive power steering systems. Remember, you have to add oil to the .3 oil to your power steering system. There you go. Brake systems, advanced braking systems combine hydraulic force with electronic control for safety. So here's hydraulics again. Marine industry, industrial robots, arms, and all that stuff. So there you go. You can read English. Go ahead. Now we're going to talk about a little bit about sensors, different types of sensors. Now the sensors could be position and motion feedback. So position and motion feedback. That's what the sensors give us. Sensors monitor the exact position of hydraulic actuators. We talked about that in the last couple of slides, such as cylinders or robotic arms. And they can send the signals to the controller. This allows for accurate movement and smooth operation, blah, blah, blah. Okay, pressure and flow monitoring. There are pressure sensors. So as one thing is controlling where the piston is, or monitoring the positioning of the pistons, but you can also go a little bit further. You can control the or you can sense the pressure. You can monitor the pressure. Pressure sensors and flow sensors continuously check hydraulic fluid conditions. If pressure drops or exceeds safe limits, then the systems can adjust or shut down to prevent damage. One of the real-world applications would be the sprinkler systems, the fire sprinkler systems. You can see them all over the place. How they work, they do have pressure sensors in the main distribution type of a panel for a sprinkler system. And the sprinkler systems, well, this course is not about that, but I'm going to give you a real-life application. So there are wet and there are dry systems. So in the wet system, the pipes are filled with water and the water is under pressure. If one of the sprinklers is broken because of fire or something like that, well, usually with fire, or somebody breaks it with a ladder, then the pressure drops because there is water squirting out of that sprinkler. So that automatically makes the pressure drop, and inside the main panel the pressure drop is being sensed, and that triggers the communicator, which sends the signal to the monitoring station, and the monitoring station is going to receive that signal, and they're going to maybe they're going to call fire department or something like that, right? Error detection and safety. Sensors detect leaks, blockages, or actuator malfunctions, and so on. So alarms and corrective actions can be taken. Integrating with PLCs, sensor data feeds into the programmable PLCs, which we will be dealing with in a couple of weeks, enabling advanced control strategies so the sensors can send signals of how things are happening. And so, well, that's the actual what do you call it? Function of the sensors. They sense, but so what? They sense signal. They have to communicate with something else to inform whether the condition of the whatever the machine is working is good or something is wrong. Energy efficiency. Okay, here's the eco thing here. Now this is example of what the electromagnetic flow meter looks like. Well, that's what it looks like. Now flow sensors. So here's an example of a flow sensor. Here's a magnetic piston. If there is a flow through this pipe and it goes that way, then it's going to push that thing out. And oh look, here's a magnetic piston. I'm going to zoom in a little bit here. See, here's a magnetic piston. There's a flow of the fluid going this way right here. Here's a piston. That piston is going to be pushed out because of the flow, by the power of the flow. So that thing is going to be pushed out. Here's a magnet. Here's a reed switch. See that? it closes based on the magnetic field being present, and it's going to keep informing whatever the processing control unit that there's a flow going on. As soon as the flow stops, that spring is going to push it down, switch is going to open, and that can cause all kinds of alarms that can be used to take some corrective actions. Oh yeah, there you go, see? That's what, oh look, yeah, here's the open and there's this close position, look at that. Okay, now here's a symbol for the control switch or the flow switch. Normally open or normally closed flow switch. Whoa. Okay, flow sensors, primary role, functionality, output. So we talked about that just like a few seconds ago. Often a simple on and off signal or basic flow rate indication. So that would be on and off signal. You see, we talked about the binary systems and the logic gates today a little bit. Those gates or any kind of system that works in a digital format can be fed high or low signal, and something is on, something is off. Right? So that will be pretty much output of those sensors. Unless it's a little bit more complex system, then it can give you some more information, but then it will be some kind of, you'll be using some sort of a communications protocol to send a message to the whatever control unit. Applications, okay, there you go. Primary role, measure, and functionality, output, continuous analog or digital readings. All right, so there you go. So flow meters, flow sensors, and flow meters here, sorry. Here's a primary role, So flow sensors is going to tell you that something is flowing in a pipe. And the flow meters is going to actually give you some more exact measurements of what's happening here. And over here, the sensors will tell you something is happening, and this one here is going to tell you how much of it is happening, or how fast things are flowing. What's the flow of flow rate? For example, liters per minute or gallons per hour. Some examples: applications, industrial process control, billing systems, performance monitoring, and all that stuff. Okay. Hardwired logic. Okay, so that's what I want to talk about here. Now, I'm going to skip that slide and I'm going to come back to it. In 1970s and part of 80s, the process control on production lines would look like this. These are a bunch of relays connected together, and they will be hardwired. So in order to set up some sort of something that's called hardwired logic, see here, hardwired logic. And this will be a elevator control system. I just grabbed that picture from the internet. There's a reference there somewhere. There you go. How does whatever the machine is supposed to operate, it is, the control system is assembled, carefully designed, hardwired, that's it. If you want to change something about how this is supposed to work and respond to any kind of signals, you would have to get the schematic, and you have to extremely high qualified person to do that. Plus, that person will have to know that system, that particular system. And the change can be made, so there will be downtime involved. If there would be like a car production line, in order to come up with a new model of car hood or any kind of thing that has to do with the car body or anything that has to do with production line, The downtime would be months to rewire things, test things, verify everything is fine. Now, as opposed to programmable logic. This is actually the PLC module that we will be working on in our lab. It has brains and it has hardware. It has a bunch of outputs. Yes, you're going to have to accommodate some sort of hardware to place a robot arm here, place a robot arm there, and everywhere. But in order to control the process, you send a program into the PLC, Programmable Logic Control module. And if you need to change something, you change the program. So, well, so here's the difference between a hardwired logic and a modern PLC or programmable logic control. Now I'm going back to that slide before. Hardwired logic versus programmable logic. Hardwired logic. Control logic implemented using physical wiring, relays, switches, and contactors. It's a fixed design. Once wired, changes require rewiring. Simple and reliable for basic operations. Well, you can't have a virus in it because there is no software. No software involved. Purely hardwire based. Advantages: high reliability in harsh environments. No risk of software bugs. All right. Disadvantages: difficult and costly to modify or expand. Limited flexibility and complex sequences for complex sequences. Typical use: older automation systems, simple machines, safety interlocks. Still being used, but not on high on the high-end production lines, for example. Programmable logic. Okay, definition. Control logic implemented in software using programmable logic controllers, PLCs. Flexible. Logic can be changed by updating the program. Supports complex operations, sequencing, and integration with sensors. Sensors can be added, they can be repositioned, data can be interpreted in different way, whatever. Advantages: easy to modify and scale. Can integrate with advanced features like networking and data logging. Disadvantages: requires programming knowledge. If that's a disadvantage today, I don't know. Higher initial cost compared to the hardwire systems. Initial cost. But comparing the cost of a downtime of production line for months, whether this could be a couple weeks, then there you go. Typical use: modern industrial automation, robotics, process control. All right, so summary for this here. Mechanical power transfer uses solid machine parts to transmit force and motion directly for the mechanical power transfer. Key components: shafts, gears, chains, belts, cams, and levers. Key points: highly efficient for precise control and speed and torque over short, here's the thing, here's the cost you have to pay for it, short distances. Short distances, we're talking about couple meters, maybe. How long is your car? As opposed to kilometers. Rigidity, there we go, provides rigid transmission, but it's prone to wear and tear and slack. Here's a backslash. It's in complex systems. Have you ever seen inside of a Swiss watch? Well, me neither, but I know someone who did, and he told me a thing or two. Okay, it's complex. Maintenance requires regular lubrication, maintenance, and physical parts to prevent breakage. All right, so this is mechanical power transfer. Electrical power transfer. Here's a summary of what we did. Method: converts electrical energy into mechanical energy through motors or solenoids, electromagnets, right? Key components: wires, transformers, generators, electric motors. Key points: control, highest precision and easiest integration with digital control systems. We're talking about the electrical power transfer, right? Cleanliness, it's a cleaner than fluid. Right? No leaks, electrical. No oil leaks, and often more cost effective for intermittent use. Yeah, whatever that means. Limitations: lower power to weight ratio compared to hydraulics. All right. Less effective for extreme shock loads. All right. So that was electrical, pneumatic. Pneumatic. Is that what we did? Yep. Electrical, pneumatic here. Okay, let's go. Methods uses compressed air or inert gas. What's an inert gas? Non-reactive, not chemically, doesn't explode, right? As the medium for the power transmission. So the medium that's used for the power transfer uses gases. Right? Key components: air compressors, storage tanks or receivers, FRL, filter, regulator, lubricator. We talked about that during the labs. Sometimes, most of the time, you're going to have filter in the main service unit. You're going to have a regulator. Sometimes you will have the lubricator and sometimes not. Because sometimes you want the little tiny bit of a oil mist in the system, and sometimes it works against you. So, and pneumatic cylinders. Right? Key points: we have fastest response, pneumatic. Fastest response times, ideal for quick, repetitive movements and high cycle tasks. Safety, safe for hazardous or explosive environments. Leaks are non-toxic, it's just air. Right? Performance, lower force capacity due to the compressibility of the air. Less precise, it's less precise for mid-stroke positioning, so it's the most efficient for fast, fully extend and fully retract. That's what pneumatics are good for. Now, where it comes to hydraulics, you can extend that here and stop. You can extend that here and stop, and you can go back. So that's hydraulics for you, and this is this would be the pneumatics. All right, hydraulic power transfer. Looking at the time, we got 4 minutes. Method uses pressurized incompressible fluids, typically oil, to generate and transmit immense force, huge force. Right? Key components: hydraulic pumps, reservoirs, control valves, directional pressure and flow. It does have directional pressure and it does have a flow. Okay, good. And actuators and cylinders and motors. So there will be key components and key points. Let's hear. That's a hydraulic. Power density unmatched for heavy duty applications requiring extreme force and high torque, but at low speeds. Precision provides smooth, vibration free, because it's incompressible, and rigid, tough control, because liquids do not compress. Drawbacks: risk of fire, we got a risk, or environmental contamination from oil leaks. Requires a larger physical footprint, so the machines look bigger for the power pack. Okay. Now here's a bit of a comparison table. Here's a feature for pneumatic, hydraulic, mechanical, electrical systems, which is basically what we talked about. So you can go over that. Here's the same thing, but there's a different look, different perspective on that. I'll leave it with you. You have it already downloaded. And we're going to have some questions that we're going to tackle next time we see each other in person. So this will be the questions, and there will be some answers. I'm going to... do I have time? 2 minutes. All right. So question number 1. Let's see here. What would be the 4 primary technologies used for power transmission and for the 4 primary technologies for power transfer? Can anybody come up with one? Just send me a text, or you can pipe in voice if you want. We just talked about that. Okay, pneumatic. There you go. All right. Anybody else? What will be another one? If you want to go on, okay, mechanical. All right, cool. We got 2. I will match you with the other 2, electrical and hydraulic. There we go. Good. So hey, look at that. It is true. All right. All right. Bouncy things. Okay, good. You guys are paying attention. Question number 2. Which power transmission system offers the highest force and smooth motion control? There's only one that excels in that. Give me one. Hydraulic. Okay, good. Yes, it is true. All right. You have that already. Don't read that. If you're reading it, please don't. I just want you to, because you're cheating yourselves. And do we have time for one more question? All right, one more question. What is the main working medium for pneumatic systems? Hey, compressed air. Good. We're going to take a look at some other questions later on. Okay, that's it for today, guys and gals, ladies and gentlemen. Thank you for your attention. As I say always, you people are wonderful. I shouldn't say you people. You guys and gals, ladies and gentlemen, you are just wonderful, but not as wonderful as me. And on that happy note, I gotta stop this class because I gotta get ready for the next class, and Zoom is going to take some time to process the video information. Thank you, and I'll see you next time.